motion planning of a car. So this will be example one. I will show you how to do this also for a manipulator. Okay, so here's the car, and then there's a goal, x, g, y, g. And let's say that we have some obstacle on the way. That would be B. And then we'll choose some rho 0. So what we'll do here is we will write the same attractive and repulsive field as we have done before. Okay. Then we'll take the derivative of, to compute the force, it will be du negative gradient of du be du attractive minus du repulsive, which is nothing but f attractive plus f repulsive. So what we can do is we can individually compute those, find the force. Now the question is, how do you take the force generated from this potential field and transfer it to control the car? Okay. So remember, we have two controls. Those are V and I think it's omega, right? V determines the speed at which you are going towards the goal, this V. And then omega determines the rate of change of the angular speed. Okay, so how do we use this? Well, just like the go to goal controller, we just choose some V nominal. Okay, because that force, we don't really need to control the speed based on there's an obstacle or not, but we'll use this to give us a heading. So we want a theta desired, which is the desired heading, and we can actually use the fact that this force in some way corresponds to the direction which we want to go. So if you take the tan inverse of f, this f, then that could be a potential way you can head. So the force, if it's attractive, it's going to just go straight to the goal. If it is repulsive, it's going to go away from it. And then given that, we can use the same controller we used for the go to goal. It's going to be k times theta desired minus theta. K times theta desired minus theta, where theta is something which you'll know, it's this angle. So this theta desired goes here, and this k is user chosen. That's it. So we're just adjusting the heading so that we can get the robot to go to its goal. Okay, so let's see how do we take this idea, which is very similar to go to goal in terms of approach, getting a theta desired and doing, but the calculations are different, and see how it works. So the code, see what's changed. It's quite a bit of code. A lot of this code is about doing the animations and things like that. So I took the code which I wrote down for the go to goal, so it's very similar, and just changed some things like, for example, you see that there is an attractive force which inputs of x, y, x goal, y goal, and then the free parameters which you set, user chosen parameters. So it computes the force and sends it back. There's a repulsive field which gives you, which needs x, y, all the obstacle, and then the constants. Okay, so it computes f rep, y rep. And then in the formula, so let's just go to the attractive field first. So what I'm going to do is I'm going to shut off, obstacles are off. So I put 0. And let me just run this with the obstacle, and then I tell you what the code is doing. Okay, so black dot, the robot is heading towards it, no problem. The thing which I did here was that in the main, so this is the main, well, not Euler integration, but down below. Okay, so this is where the code start. I take parameters, direction. Again, I don't think I need this. This is an extra. Let me run this. I don't think this is a leftover from that other earlier code. Yeah, it doesn't. It's not needed. Okay. Okay. The only thing I'm doing here is computing the attractive force, attractive, and then I stood down the formula, right? Theta desired is Fy divided by Fx. V is set to nominal, and then here uh, omega is k times theta desired minus the same formula I wrote. Okay, that works. Now let's turn the obstacles on. Okay, and the way I did created the obstacle is there in the parameters. So the obstacle I have basically the location of the obstacle 1 1, and then the size of the obstacle is 0.2. Okay, and by the way, we can change the goal right here. The goal should be, yeah, x goal, so it's 1.5 1.5. So let's run this first. Okay, we could change this 0.3, so bigger obstacle should still work, I hope. Okay. Okay, so you can see that it wiggles there because of the way the potential field is. It tries to find a location where the potential is minimum at that location, and then that causes that wiggles. Now you could fix this in the following way. If you know a trajectory, you could then smoothen it out, and there are ways to do it. But let me not get into the details of that. You could also move the goal. I'm going to move it slightly to the right and see what happens. It's a small turn. You could also introduce more obstacles and get this to work. But the change which I made here was I looked through all the obstacles. Here there's only one, but you could actually put multiple obstacles here. It'll work just as fine. So I look at all obstacles. I find the center. Where's that? Right here. Yeah, if obstacles are on, then I find the center, which comes from that list. Then I actually have commented out the go to goal. You can turn it on if you want. I find the repulsive field for each obstacle, and then I just add it up. Okay, and then I get the desired angle. Okay, so if you want to add obstacles, let me see if I can do it quickly here. So if you want to add obstacle, all you do is say you want to add extra obstacle at 1, 1.5, 0.2. So this is giving you x, y, and the radius. Okay, maybe I should have added the obstacle on the right. So let me change this. Since it's going right, I'll put an obstacle right there and see if it works. So let's change this to 1.5 and then move this to 1. So now it's going to be on the right side. Let's see if it struggles or it goes. Okay, now it's going to struggle. Okay. Okay, now there's no good reason why it should turn right, it should probably turn left, but all these planners are local planners, which means that they do not have global information. They just look in the vicinity and make decisions based on that. A smarter way to do this is, let's say that if you knew, if you had bird's eye view and you knew everything about the obstacle, you could actually plan a better path. So this is what they call a local planner. We'll only do local planners in this course, but there are global planners which basically use some kind of information from all the obstacles and radiuses to make a plan. There